what we get is 6.1837%. There's not too much of a difference between daily and continuous compounding. A lot of times your bank will say interest is taken out and then compounded daily, it's fine, you're not missing out on much. You do want to, if you can at all possible, focus on instruments that are going to give you continuous compounding, like CDs or savings accounts. You don't want any of the others. We can also calculate the continuously compounded rate of return on the stock for some period as follows. If ST is the end of the period, so the stock price at expiration, and S0 is the starting price, then the continuously compounded rate of return is going to equal the natural logarithm, and that's just basically the inverse of this exponential function, the natural logarithm of ST divided by S0, or the natural log, where ln is the natural log. So again, if we look at this, let's look at a simple example. Let's say 120, and the beginning value was 100. And in Excel, this is just ln, so natural log of ending divided by beginning. So what you can see here is $100 compounded annually for a year at an 18.23% is going to get us to 120. Pretty much the example I just did. So this is the APY, right? This is the annual percentage yield that yields the actual effective yield of 10%. That's all we're really looking at. Now, that's only important because we're going to be in the Black-Scholes model, and this is, again, one of these Nobel Prize models that you should be aware of when you go out into the industry. It's only important because that's how we're going to be discounting. So instead of just a simple discounting, right? And by simple discounting, I just mean what is 1 divided by RF per period. So I'm just doing that individually by period. With the Black-Scholes, we're going to use continuous compounding. Models of stock price movements. Let's get the frame. All of this is somewhat relevant, not extremely relevant. The perfect model would indicate the exact future price. That would be nice, unlikely. Probabilistic models, what we've kind of been working with, this is going back to our examples of different states of the world. If the state of the world in a boom state is 25%, and then we have an expected return for a boom state, and the state of the world in a normal state is 50%, we have a return for the state of the world that's normal. These are probabilistic models. We're assigning a probability to the state, and then assuming an outcome for each state. Binomial model, what we've been looking at up until this point, with binomial trees. Only 2 outcomes are possible, and in each outcome, the stock either moves up or it moves down by some constant amount or some percentage amount that we've been working with. The Black-Scholes, in all of its wisdom, says that the evolution of a stock price over time is governed by geometric Brownian motion. And since most of you are business majors, I wouldn't expect that you actually knew what geometric Brownian motion is. I didn't. Geometric Brownian motion, if you look it up, is crazy.
Sounds like something you do in the bathroom.
Let's take it. look.
Casting process.
And usually our best place to look is on something like YouTube.
Just be little fingers.
Geometric Brownian motion describes a particle that's acted on by random particles, basically as this is hanging in a solution. So as electrons bounce off of something, they're basically random, but what happens is it's kind of random with a direction. So like as more particles hit on one side, it moves, but you can't really predict it. And all it says is that the possibility of this moving very far in one direction is small, because all the balls aren't banging in one direction, just like the possibility of moving in a direction is small. And this kind of goes back to some sort of sense of normality. Depending on how fast these balls are banging around, that's the volatility. So if we look back at our example, if we were able to somehow speed this up, if we speed up these balls, and they kind of do this throughout the video, the more speed, the more volatility that you introduce into this, the more likely it is to have larger movements. And so if we take a look at this, when we're increasing our volatility, the likelihood of a change, and these are just the likelihoods of change of 2, 5, 10, and so forth. And then comparing the different volatilities, we can see, do you guys want to keep talking, or do you have something you want to talk about?
Me?
Yeah? No? Okay. The likelihood and the volatility, as we increase the volatility, the probability of greater movements becomes more frequent. Higher volatility then, as we've seen, this implies that the stock is riskier, but it also means that there's going to be more higher future price changes. And they're higher future price changes because you can only have higher future price changes in one direction. You can have more than 100% gain, but you can't have more than 100% loss. Again, just working with some of the distributions we've kind of familiarized ourselves with. A probability distribution, or a density function at the top, approaches normality. Stock prices are this more skewed distribution. We have a long tail out to the right because we can have 1,000% return. As we take the log of this, it approaches normality. So this is called a log normal distribution. And again, with geometric Brownian motion, and this is what most people have relied on, it predicts that large price movements will be far less likely than is in fact the case. And we've seen extreme instances of this. So we saw the stock crash of 1987. We saw the flash crash of 2010. And if we basically just assume a 20% volatility level, which is the average of the volatility, the average standard deviations for stocks over the last 100 years or so, the probability of this is basically 1 out of 1 trillion years. There's also evidence that returns do not scale the way they should. Returns should be proportional to elapsed time and standard deviation, but we know that this isn't the case. And there's evidence that monthly and quarterly volatilities are too high. All of this basically saying we don't have a great model, but the best model that we have is the Black-Scholes formula. So this is the second part of the project, and all this really says is the call value is equal to the stock value times some probability. And we'll talk about D1 in a second. minus e to the RT. And one thing that you could probably see from this, and we'll talk about how you actually get here in a second, but one thing that you could see from this is that as time to expiration decreases, as t becomes a 0, we're multiplying r then also by 0. And so this whole formula reduces down to essentially stock minus strike. So what we're coming up with is we want to know how much the call value exceeds this intrinsic value, the stock minus the strike. And what we have in that is these D1s and ND1s, and you don't really need to understand the complexity here. More of the intuition that we've already talked about, kind of what goes into these formulas. But it's worthwhile looking. D1 is an adjustment for how much the stock is in money, right? Natural log of the stock price divided by the strike. So that's the continuously compounded rate of return that the stock is either in the money or out of the money. Then we have an adjustment for the risk-free rate, which we saw determines stock price, volatility, and a correction by volatility in time. All that really means is where is the stock in relation to the strike and how volatile the stock is. And D2 is just another correction on D1. So, what we would want to do in the project is we want to set this up. I would set it up on a new sheet, and I would say stock, strike, volatility, risk-free, and most of these are all the same. And then what you need to do is same way, set up D1, set up D2, and set up the call price. And again, I think we had 75, 75, 25, and this was 5%. Each one of these requires a formula, so you would just go into D1 and you would say, yes. So, making sure that you get the formulas right here is the main point. D1, it's worthwhile to probably put a parentheses around the whole numerator and the whole denominator. So, natural log of stock minus divided by strike plus the risk-free rate, the volatility squared divided by 2 times the time. And in this case, it's just a 1, but let's just say times down here. And D2 is easy enough to figure out. D2 is equal to D1 minus volatility times the square root of time and then we put in the call value. So the call value is equal to the stock times, now that ND1 in the formula is the norms disk. And all this tells us is that under a standard log normal distribution, how many standard deviations away is D1, this value, minus the strike times